Okay, so the next thing that I would like you to do, or like us to do, is to start to make that transition between thinking about lines, which has been our focus for the last 5 weeks, into triangles and seeing how there's a connection between the two. So I want you to think about this first of all. So, say you had a 20 kilogram box that you had to push up a ramp. And when we look at the ramp, we can kind of think about it as a right angled triangle. So we've got our right angle here, a right angle here. Across from that is a hypotenuse, and across from there is the hypotenuse. And then we also now, if we wanted to label the other sides, we know that this would be the opposite, and this would be the adjacent, and this would be the opposite, and this would be the adjacent from the angle that the box is sitting at. Okay, so we're going to take this 20 kilogram box, we're going to push it up the hypotenuse of a triangle. And I want you to think about, if you had your choice, which hypotenuse would you want to push it up? Would you want to push it up the hypotenuse of triangle A or the hypotenuse of triangle B? Okay, so think about that for a second, and then we'll talk about the advantages and disadvantages of both. Okay, triangle A. If you're going to push it up triangle A, there's probably two things that you'll notice. So first of all, triangle A has a hypotenuse that is longer than triangle B. So if you're going to push it up this ramp, then the hypotenuse you're going to push it a little bit further because the hypotenuse is longer. So that's a disadvantage. However, if we look at the angle here that it makes with the ground, and the hypotenuse overall is less steep because that angle is lower than this one right here. So this one has a disadvantage of being a longer hypotenuse, but an advantage in that it's not quite as steep. So it's going to be a little bit easier to do. You're just going to have to do it for longer. Whereas this triangle B right here, you've got a shorter distance to go, which could be an advantage. However, the angle is bigger, it's steeper, and it's going to be a little bit harder. So you've got a shorter distance and a harder push up the triangle. So you could argue either one, but just thinking about kind of that connection there. And if we connect this, like I said, back to our work with lines, one of the things that you'll notice is that if we're talking about steepness, it's kind of like talking about slope. And if we were going to calculate the slope here, what we would do is we would talk about the rise and the run. So I know that the slope here has a rise of 3 meters and a run of 11 meters. So you're going to run 11 meters and rise 3 meters to get from the beginning to the end of this. And that would tell us how steep that line is. Okay. This one over here has a rise of 3 meters, just like this one. However, the run is only 5 meters. So here I have my rise over my run of being 3 over 5. Okay, and again, that's going to tell us our steepness. So if we actually take a look at those numbers, so if we calculate the rate of change for this triangle right here, rise over run, we can connect that to the language we've just used to help us label triangles. So the rise is over here, that becomes our opposite side, and our run becomes our adjacent side. So the rate of change is rise over run, which is also equal to opposite over adjacent, and the opposite side or the rise is 3, and the run or the adjacent side is 11. So 3 divided by 11 is 0.27. So the rate of change for this triangle is 0.27. Similarly, the rate of change for this triangle, rise over run, again connected to the opposite and our adjacent. The rise over run is equal to opposite over adjacent. The opposite side is 3, which is our rise, and our run, which is 5. And when we take 3 divided by 5, we get 0.6. So now we can just verify, if we look at the rate of change for this triangle and the rate of change for this triangle, this one is going to be steeper, which will make it a little bit harder to push. However, it's going to be shorter. So we've got to take our advantages and disadvantages. Okay. But what I wanted to point out to you is that this connection between rise and run and opposite over adjacent is actually a really common calculation that people make. And in fact, it's so common that they've given it a name. They call it the tangent ratio. So anytime you see a triangle and you're calculating the opposite divided by the adjacent, and using that to connect to an angle, we call this ratio opposite over adjacent. We call it tangent, okay? And it's got a really neat property. And the really neat property is that for the tangent ratio, and again, this connects back to some of the work we did with similarity as well. When we talked about similar shapes earlier in the semester, we talked about how similar shapes are basically growth or decreases of each other. So we had growth factors that we multiplied to get bigger shapes. We had decrease factors that we multiplied by to give us smaller shapes. And we know that even if they were bigger or smaller, they still had that same angle. Because all similar shapes had the same angles within them. So if we think about this tangent ratio as being similar triangles. So let's say I took a triangle that has a 9-degree angle here in the corner. It has a 37-degree angle in this side right here. But it took different kind of growth and scales of it. So here's the medium triangle, here's the small triangle, here's the big triangle. All of these triangles are similar because they have the same angles. They're just different sizes of each other. But the really cool thing is that if you look at the opposite and the adjacent sides of those triangles, that tangent ratio, opposite divided by adjacent, will always give you the same number. So if I look here, I'll start with a small one. 37 degrees is our angle. And if I look at the opposite, I get 3. And I look at the adjacent, I get 4. So when I take the opposite and adjacent side to this triangle and divide them out, the tangent ratio for 37 degrees would be 0.75. If I look at my medium triangle, it's the same thing. If I take my opposite side of 6 and my adjacent side of 8 and I divide them out, I get the ratio of 0.75 again. So the tangent ratio for 37 degrees of this triangle is also 0.75. And finally, for our big triangle, the same thing holds true. If I take the opposite side of 9 and divide it by the adjacent side of 12, that ratio is still 0.75. So it doesn't matter how small or how big this triangle is, as long as it's a right angle triangle that has the angle of 37 degrees here, the tangent ratio, opposite divided by adjacent, is always equal to 0.75 or approximately equal to 0.75. Okay? And the neat thing is we can take this relationship, and I'm going to pull up a little app here if I can find it right here. And we can look at this ratio opposite over adjacent for all angles. Okay, so I'm actually going to start here. Let's start at 40. Actually, let's just start down here at like 1 degree. Okay, or actually, we'll start at 5 degrees. So here I have a triangle. I have my right angle triangle, or my right angle right here. And I have my angle that I'm measuring right here. So this is the angle I'm working with. My opposite side is going to be across from it. My adjacent side is going to be beside it. And you can see here the applet's actually showing you that the opposite side is 0.806. The adjacent side is 9.211. And when I take the opposite and adjacent ratio and divide it out, I get 0.087. And what I can do then is I can take that angle and I can change its side, and I can make it bigger. Sorry, change the angle, make the angle bigger. And you can see below the adjacent over opposite over adjacent ratio is changing as I change the angle. So that ratio is going to be, you can keep going and going and going all the way up to pretty much 90. Okay, so the ratio of the opposite over adjacent is unique for every angle that you could possibly have in this right angle triangle. Okay, and what somebody did way back in history is they basically took this property and they created a chart. And this is a chart. It's located on the course document. So I'd like you, if you can, to print it off. And if not, there's a link that you can use that also contains the chart. But this chart basically summarizes what all of those ratios are for all the different, well, not for all of them, but for many of the different angles that you could have within a right angle triangle. Okay, so for example, I'm going to show you how to read this. So let's say I had a right angle triangle and it had a 20-degree angle in it. And I wanted to know what is the opposite divided by the ratio, the opposite divided by the adjacent ratio. What is that equal to? So if I took a 20-degree angle in the right angle triangle and I measured the opposite side, and I measured the adjacent side, and I divided it out, I would get 0.364. If I took a 25-degree angle, right angle triangle, and I took the opposite side from the 25 degrees and I divided by the adjacent side to that 25 degrees, what I would do is I would look, so here's my 20, here's my 5, so I would go to the square that connects those two right here. The opposite divided by the adjacent ratio would be equal to 0.466. So all of those ratios of the opposite divided by the adjacent for all of the integer values of angles are listed in this chart. If I wanted to see what the ratio would be for 82, I would go down to 80, I would go across for 2, and if I had a right angled triangle and I was going to calculate the opposite over adjacent for an 82-degree angle, then that ratio would be equal to 7.115. Okay, so somebody has done some really precise calculations and they figured out this table that summarizes all of the different tangent ratios, all the different opposite over adjacent ratios for these angles listed in, or that could exist in a right angled triangle. Okay, a couple things that I want to point out. First of all, it starts at 0, and as you can imagine, if you had an angle of 0, you wouldn't really have a triangle anymore. You wouldn't have any rise. That's why it's 0, because 0 divided by whatever your length of your adjacent would be 0. So it starts at 0. And you'll notice here that it ends at 89. And it ends at 89 because if you think about a right angled triangle, we know that all triangles add to 180. We've got a 90-degree angle that has to be there in order for it to be a right angled triangle. So 80 minus 90 is 90. So basically we have 90 degrees left over to split between the two other angles. So if we had this chart go over 90, we wouldn't be able to really do that because the triangles then would go beyond the 180 degrees. So the chart starts at 0, which kind of is a bit of a weird one because it doesn't have a rise, and it ends at 89 or just before 90 because we can't have more than 180 degrees in total in those triangles. Okay, there's another neat one that I want you to look at, and that is the idea of the 45-degree angle. And if we think about a triangle that has 45 degrees, I'm just going to take you to a triangle that has 45 degrees. So this is a right angle triangle. It's got a 45-degree angle here. Let's just say that this is the one that we're working with. We know then if the whole thing needs to add to 180, we've got 90 here, we've got 45 here. That means we have 45 degrees left for this side. What we actually create here is an isosceles triangle because we've got these two sides. These two angles are the same, which means that these two sides would be the same. And if you think about it, if you take the opposite side and divide it by the adjacent side for an isosceles triangle, if you take a number and divide it by itself, you're always going to get 1. So if this was, say this was 8, then this side would be 8, this side would be 8. Opposite divided by adjacent would be 8 over 8, which would be equal to 1. If this was a bigger triangle, let's say this was 100. So if this was 100 centimeters and this was also 100 centimeters, opposite over adjacent, 100 divided by 100 would give you 1. And if you look in our trig table, you can actually see that. Actually, I'm going to put on this one right here. If we look at our trig table here at 45 degrees, you can see that the triangle would be, or the ratio of opposite over adjacent would be 1. And that's because for a 45-degree angle within a right angle triangle, the opposite side needs to be equal to the adjacent side. Okay, so what I would like you to do now is I'd like you to take this chart, and if you don't have the chart, just pull it up on your screen, and you can do this on a separate piece of paper if you don't have a printer. First of all, at the top of this page, I did label the triangle, just again how to label the triangle. So if I have a right angle triangle and I'm calling this my theta, my angle that I'm working with, the hypotenuse is across from the right angle, the opposite is always across from the angle we're working with, and the adjacent side is the one beside the angle that's left over. So I've got my little diagram there just to remind myself that I'm looking at opposite over adjacent, And now I'm going to use this table to find ratios. So if I say to you, find the tan of 70 degrees, what you're doing is you're looking at 70 degrees. So I'm going to go to 7 and 0. So it's right here. I've circled it in green. And the ratio of the opposite over adjacent, the tangent, is equal to 2.747 approximately. So I'm going to write that ratio right there. Okay, so for the rest of these, kind of turn this off for now, see if you can figure out what these ratios would be equal to. Okay, you can also work backwards in this table. So for example, if you have the tangent of some angles equal to 3.271, then what you can do is you can look for that ratio in the table or something close to that ratio in the table. So when I look in this table, I see that ratio right here. There's our 3.271. And I can see that the angle 73 is connected with that ratio. So if I know that the tangent of some angle is equal to 3.271, then the angle that must go with it is going to be 72 degrees. Okay? So again, you can look for those ratios in the table, work backwards, and get the angle. Okay. My hint to you here is that if sometimes you'll see the exact ratio, like we did for that first one there, the exact ratio. But let's say this was 3.3. Well, 3.3 isn't exactly on the chart, but it's pretty close to 3.271. So I can say, you know what, if it's 3.3, that's pretty much going to be 73 degrees, maybe a little bit more. Okay, so you can use that table to work backwards to find the angles. So the last thing I'm going to ask you to do today is to kind of turn off the video, see if you can find the ratios for the top 6 and find the angles for the bottom 6, and then come on back, check your answers, and we'll carry on from here when we begin again in the next lesson.